and she will tell us something about recommending for a multi-sided marketplace with heterogeneous contents. Stage it.
Thank you. Hi, everyone. This is Yuyan. Is the slide up? Okay, great. Sorry about that. Thank you for the introduction, Hannah. So today I'll be talking about our work on recommending for a multi-sided food delivery marketplace with heterogeneous and hierarchical contents. Can you hear me fine? Okay. And this is a joint work with Long and Xian at Uber. So I'll go to the background and introduction for now. And with this audience, I don't think I'll really need to introduce recommender systems and how popular they are in our daily lives already. So indeed, on one hand, recommender systems, they facilitate information acquisition and decision making for the users or the customers. And on the other, they help the firms to target prospective users without the need to spend extra on advertising. And in particular, in this work, we focus on one particular type of recommender systems, and they are food recommender systems. So to give a sense of the problem space that we are working with, the food delivery industry has been growing really fast during the past years, especially during the pandemic period. Like I myself rely very heavily on food delivery apps during those times. And in this work, we basically consider building food recommender systems for those food delivery apps. So how can recommender systems help in this case? On the left here shows a word cloud I generated using some of the popular restaurants available in San Francisco in the Bay Area. So imagine the homepage of a food delivery app looks like this. Will this help you decide where to order for food today? Probably not. So this is where food recommender, thank you. This is where food recommender systems come into play, where we basically show the most relevant products, in these cases restaurants, to the users and with the right context and at the right time. So this is the problem space we are working with. And then if you think about this problem, although recommender systems are very common in our daily lives already, but recommending for a food delivery marketplace has its interesting and unique challenges. So in case you're not very familiar with it, the way that a food delivery marketplace works is that the users or the consumers will first place an order on the restaurant through the platform, and then the delivery partners, or sometimes we call them couriers, will go pick up the food and then deliver to the users. So this essentially formulates a dynamic three-sided marketplace where each side is either the business's customers or their consumers. So in other words, we would like to keep all three sides happy in order for the business to be successful in the long run. But however, different sides may care about different objectives, and recommending in this context usually entails jointly optimizing multiple objectives that are potentially conflicting with each other. So in other words, trade-offs naturally exist. So this is the first challenge we're faced with. And then a second challenge comes from the fact that a lot of the food delivery apps will choose to present their recommendations in a hierarchical way, in the sense that a recommendation can either be a single restaurant or a group of restaurants. So for example, on the left here shows the homepage for the Uber Eats delivery app, where we can see both rows, or we call them carousels of restaurants, that can be scrolled horizontally, as well as single restaurants or standalone restaurants that are appearing as single rows. So in these cases, the homepage is essentially a two-dimensional grid consisting of heterogeneous and hierarchical products, and as a result, off-the-shelf recommender systems are no longer applicable, as they mostly focus on recommending homogeneous contents in a one-dimensional list. So to summarize, in this work, the research objective is to design a recommender system for a food delivery app that can simultaneously tackle these two challenges. And then the next, I'll present our proposed methodological framework, which is a multi-objective hierarchical recommender, or MORE as its acronym. So on a high level, this framework is a three-step procedure combining machine learning, hierarchical modeling, and multi-objective optimization. So in the next, I'll zoom into each of the steps separately. So for the first step, we call it multi-objective prediction. This is where we take the user information, restaurant information, and source information, and I'll explain what source means in a moment. So we take those information and go through a list of machine learning models, and the outputs are the predictions for the restaurant level objectives. So in particular, remember we're in a three-sided marketplace, so we built separate machine learning models to estimate these different objectives that we care about. And they include user conversion and retention as the user level objectives, basket value as the company level objectives, and then marketplace fairness as the fairness objective. And these predictions are done for every user, restaurant, and source triplet, where source means the hierarchy information of the restaurant. For example, if it belongs to a certain carousel or is being shown as a standalone restaurant. So by adding that extra dimension of source there, we will be able to understand and model users' behaviors with these hierarchical contents. So that's the first step. And then in the second step, this is where we do the hierarchical modeling stuff, where we take the previous estimated restaurant level objectives and go through a probabilistic module, and the outputs are the carousel level objectives. And we model an important fact in this step, which is that consumers will have limited patience when they are interacting with the app. So at any time in point, they may simply give up and if they're not finding anything interesting. So we developed this state-based consumer browsing model to account for their limited patience. And in particular, a user state is modeled as their current viewing position. For example, I'm staring at a certain position inside a certain carousel right now. And then the state transitions are Markovian in the sense that at any state, one of the following three things could happen. So the user could either scroll right and browse the next restaurant inside the carousel, or they could scroll vertically by abandoning the current carousel completely, or the final termination state is that they would just place an order on the current restaurant that they're staring at. So with this consumer browsing model, then the carousel level objectives can now be expressed as an interpretable aggregation of restaurant level objectives, which are obtained from the previous step. And this can be done by applying the law of total expectation by conditioning on the order position. And I like to point out a nice and important property for these kind of aggregated predictions, which is that they are calibrated against those for the single restaurants. Meaning that the predictions for the carousels, like the aggregated restaurants, are somewhat comparable to those for the single restaurants. Therefore, we will be able to rank them together in a mixed fashion. And this is actually critical to ensure consistent user experience across different levels of aggregation of the products, and at the same time provide levels of transparency to the restaurant partners as to why and how they are ranked at a certain position in the feed. And furthermore, this kind of hierarchical modeling can be generalized to higher levels of aggregation as well. For example, carousels of carousels, if the company decides to do so. And we just need to apply this hierarchical modeling step one more time. Okay, so in the final step, this is where this multi-objective optimization is happening, where we take the previous estimates of the restaurant level and carousel level objectives and go through a multi-objective optimization module. And this is the most math-heavy slide I'll have. So I'll first introduce some notations where we use I to index the users. Not sure if you can see those clearly, but then we use Q to index the items. And here an item can be either a single restaurant or a group of restaurants. Remember, we have those carousels. And then our optimization variable X here is what we call a ranking plan, which is a collection of real-time probabilities of recommending each item to each user. And with these notations, then the four objectives that we care about can now be written as double summations here. And then mathematically, we formulate this multi-objective ranking problem as a constraint optimization problem, meaning that we maximize one of the objectives while putting a constraint on the amount of tolerable sacrifice on the others. So written in math, it will look like this, where we have these alphas as numbers between 0 and 1, specifying the amount of tolerable trade-offs or tolerable sacrifices for the objectives. And then these star values are the optimal values for each of the objectives, which can be attained in an unconstrained manner, like without any constraints. And again, the X here is the variable we are trying to solve. So if you look at this problem, it's actually a huge scale linear programming problem that is infeasible to be solved and served online in large scale systems. So what we end up doing is actually to adopt a mathematical trick by adding a quadratic penalty to the objective function. And then by leveraging KKT condition and Lagrangian duality, we would actually be able to arrive at a closed form solution of the final ranking function, which is the X here, which enables fast and efficient serving for large-scale online systems. And I won't go into those technical details there, but happy to chat offline if you're interested. Okay, so yeah, putting everything together, this is what this framework looks like, where every step will basically take the previous step's output as its input, and then the final outputs are these hierarchical recommendations that are optimized for the three-sided marketplace. Okay, and in the next, I'll talk about some live experiments at Uber Eats, which is one of the largest food delivery platforms in the world. And before we conducted any live experiments, we realized that it could be both costly and even risky to run an extensive set of experiments on live real users without having a good understanding of the algorithms that we are having. Therefore, we first conducted some offline analysis by using this offline replay method. And it's done on random ranking data, which helps us remove any potential confoundings caused by position bias or off-policy evaluation. And for example, these two curves here shows the offline trade-offs or the offline Pareto frontiers between the several objectives that we care about, where we can see this almost concave-shaped Pareto frontier in the sense that a small sacrifice in one of the objectives could potentially lead to big improvements in the others. And then for the live experiments, in order to understand, recall that we have three separate components. So in order to understand the contribution of each of them, we designed the following treatment groups, including a multi-objective recommender, which is only the first and the third step, and then a hierarchical single objective recommender, which is only the second step, and then putting everything together. And the experiments are run as online A/B testing on Uber Eats on about 2% of global traffic. So in terms of the results, first on this multi-objective recommender, we see that by adding each objective separately to the framework, we're actually able to see Pareto improvements on the metrics that we care about. And in particular, this translates to $1 million weekly gain in terms of revenue. And then for the second step, the hierarchical modeling step, we use this conversion rate as a single objective. And we were also able to see a significant improvement on that. And even more interestingly, we have seen a significant drop in the scroll depth and search rate from the users, meaning that with this step, the users on the platform do not need to scroll as much or go to the search tab to find what they want, which means that this hierarchical modeling step not only improves the single objective that we care about, which is conversion, but also reduces the search efforts for the users. Okay, lastly, putting everything together, our full more framework is able to achieve Pareto improvements on all the metrics we care about across the board. And because of its significant business impact, it has now been deployed globally as the recommender system for Uber Eats homepage. So if you open your app today, the restaurant recommendations you see will still be powered by this framework. Okay, I believe that's all the time I have, and I'll leave my last slide on with a summary of contributions and some implications we have for this framework, and happy to answer any further questions you may have.
Thank you very much.
Thank you.
So we do have a number of questions. We will never get through all of them in time. First question to you. Sometimes people come in with an intent for, let's say, I want to have pizza today. How does your model serve to those potential items? So instead of the restaurants, you really have a targeted item that you want to search for.
Thanks for the question. I actually have 2 points I want to mention. The first is related to this work, which is, remember, we have all these carousels. So carousels actually, in a marketing term, they will view this as a potential nudges to the users to suit their specific intents or modes. Like, for example, if in this session you're looking for something fast versus something healthy versus something, I don't know, I want pizzas, but in particular, that would be something that usually the platform itself wouldn't know in real time right now. But what they can do is to potentially infer a few modes that you can possibly have and just serve you according to those modes that you will be having. So this is actually the reason why carousels exist in the first place, and that's why we propose this hierarchical recommendation framework for ranking these different carousels. And then the second point I do want to mention, which is not related to the current work. I see a couple of my current colleagues standing back there. So what we are currently actually working on for my current job is actually more related to this question, which is usually these recommender systems are based on item-level interactions. Like, for example, I consume a particular content on this platform. But we believe that in order to optimize their long-term experience on such platforms, it's actually critical for us to understand their hidden or underlying intents or journeys they're on in order for us to make better recommendations that suits their specific user journeys in the long term. So this is actually some ongoing research direction that we'll be having, and we'll be giving a talk on this at a workshop this Thursday, which is called a Review and Consequences Workshop. So please join that talk if you're interested in this topic.
I think that's a very nice closing sentence. Please answer the rest of the questions offline, and thank you very much again to the speaker.
Thank you.
Our next speaker will join us online, and it is Kohei